Okay, thank you. So I'm Sophie Cravatte, working at IRD, and I'm a tropical in situ observation oceanographer. So I'm a bit far from the community here. And Fabrice asked me to give a talk on the needs in the surface or near surface current observations in the equatorial oceans and on the limits of the current knowledge. So it's completely impossible in 20 minutes to give a comprehensive overview of these issues, but I will try at least to highlight some key processes for which I think that surface current from space with enough resolution will be able to provide insightful information. Okay, it's always useful to start by reminding why it's important to focus on the equatorial regions. So first, because it's a strongly coupled ocean-atmosphere system. And in this coupled system, the surface currents are an essential oceanic variable at the interface. And it's also key regions for climate variability with El Nino, with the Indian Ocean Dipole and the African monsoon. And these climate phenomena have impacts reverberating globally. So these are important regions for the predictability of the global system. Also, as you can see here on this map showing the annual mean drifter speed, these are regions with very strong mean currents, leading to strong instabilities and fronts. And of course, there is the equatorial singularity with specific dynamic. Okay, so equatorial regions are also interesting because we have a lot of observational challenges. So first, basically, the geostrophy and Ekman do not hold at the equator because the Coriolis parameter tend to 0. And so the satellite-based product, based on altimetry and wind scatterometers, like Oscar, Gecko, Surcouf, basically have important deficiencies, despite the whole progress made. So from my reading, I would say that they give zonal currents which are correct for scales larger than 400 kilometers and periods of 40 days, but they still have big problems in V. So to illustrate that in the meridional component, this is a map of the correlation between the meridional velocity from Gecko products and the Argo displacement. And you can see that this correlation is almost 0 at the equator. So these products are not able to give realistic meridional velocities. So we have also the surface drifters with their drop providing estimates of currents at 15 meters. But unfortunately, they diverge from the equatorial band, as you can see here on this map showing the number of drifter days for the whole period. And you see that we have very sparse data at the equator. So we lack information, in situ information. And finally, at the equator, we have moorings from the Global Tropical Moored Array. And we have current measurements at the red circles you see here. But ADCP at best sampled to 25 meters and below. And we have some current meters and 10 meters, but these are very punctual measurements with no access to the surface velocity. So with all these problems in the observations, our current knowledge on the surface currents here in the Pacific, this is the mean zonal current and EV from drifters, are quite limited. So I would say that we know very good the mean, the seasonal and the interannual variability of the signals, and we can infer the big structures at these scales. But if we look at what gives a model, high-resolution model, so this is a map of the relative vorticity at the surface during one snapshot, and here this is a time series from one mooring at 10 meters. You can see very clearly that there is a very large spectrum of variability at small scales and high frequency, which are strongly ageostrophic and that we don't have access yet with observations. So at first order, surface currents from space with a global and repeated coverage would provide improved knowledge of the current's variability at intrasonal time scale and at mesoscale, and thus new insight on the associated dynamics of the equatorial oceans. So in this talk, I will focus on two regions, on the processes in two regions. So in the Koltong equatorial upwelling region that Fabrice mentioned this morning, and on the Whirlpool eastern edge. I won't have time to explain you the processes in the highly variable boundary currents. So I will start with a region of the Koltong. So basically here you have a map of the mean SST and with overlay the mean currents from the drifters. So you have the trade winds blowing, so the Ekman divergence, and upwelling of cold, nutrient-rich and CO2-rich waters. And these are key regions because these are the regions of the largest oceanic heat gain and the largest natural oceanic source of CO2 in the atmosphere. But the dynamics of these regions are very complex and we don't understand it quite well. So you can see here on the schematic a map as a function of depth and latitude. And you see that the SST at the surface and other tracers result from a subtle balance among upwelling, vertical velocity, vertical mixing, very near shallow, mainly driven by the strong shear between the westward surface current and the eastward subsurface current, and also horizontal advection terms, which are important, especially in the presence of the front here, with the cold and warm water and very strong SST gradients. So these horizontal advection terms also influence greatly the SST. And we must have these terms right, and currently we don't. Models are not good at all to have this good balance. They don't have the correct balance, and we cannot constrain them with observations. So how could surface currents lead to progress on these processes? So first, they would allow to estimate the upwelling patterns and variability. Currently, with the observation we have, the only thing we are able to do is to estimate W. So of course, we don't have direct measurements of W, so through horizontal divergence. And we are only able to do that on the big box. So this is an example from the drifters. So we only have a mean broad-scale view from LCDCP and drifters, and we are missing the upper 15 meters where we know that 50% of the divergence occur. If we look at the snapshot here in August, you see that it's much more complex than the mean view we have, and surface current from space would, for the first time, give access to the upwelling small spatial and temporal scales. But it will not be an easy task. It will be very challenging because you can see that the upwelling variability is very important. So there have been, in the early 90s, an attempt to estimate here in the Central Pacific the variability of the upwelling with 5 moorings deployed at 1 degree around the equator. And from these 5 moorings, the authors estimated the variability as a function of time of the zonal divergence, of the meridional divergence, and thus of the upwelling. So there is a high variability in the zonal currents, mostly linked at the equator to the tropical instability waves and Kelvin waves at 30-40 days. You have an even higher frequency variability of V, mostly linked to the mixed Rossby gravity waves. And so finally, you have intrasonal variability of the upwelling at these time scales. And we don't know the spatial scales. They made the choice of 1 degree spacing, but maybe the upwelling has smaller spatial scales, but we don't know them. So surface currents from space might give insight in this problem. Surface currents would also allow to have access to the horizontal advection terms at intrasonal timescales. So we know that TWEs especially impact the heat and freshwater budget and also the productivity, as you can see here on the snapshot showing the chlorophyll. And it's interesting to look at this plot showing at a mooring a time series in 98 of, in black, oscillation in the meridional velocity, in red of the SST cooling, and in green of the chlorophyll blooms. So you can see that you have displacements of the front here leading to events of coolings and to blooms. But we don't know which part is really due to horizontal advection, which part is due to localized upwelling or convergence, and which part is due to also enhanced turbulent mixing due to enhanced shear. So we can hope that the surface current from space would help to quantify these relative roles for the SST, chlorophyll, and other tracers budget. The last point we discussed, we saw that many examples this morning, is for the ocean-atmosphere coupling at small scales. So this is a very famous plot from Shelton, showing in the same region a map of SST and a map of wind stress magnitude. So there is a strong, tight coupling at small scales around the front, and the atmosphere is responding to the SST gradients. But surface currents would provide more insight in this coupling by helping to understand the response of the ocean to the stress and divergence in the winds, and also to better understand the dynamical feedbacks and how this contributes to the maintenance of the front. Okay, let's now move to another region, which is the Whirlpool Eastern Edge. So I think that everyone knows what the Whirlpool is. It's this huge region, larger than Europe, with waters warmer than 29 degrees. So it's the heat engine of the regions. And its eastern edge at the equator, we don't see that quite well, is a region of zonal convergence. And it has been shown that this zonal displacement of these regions, carrying the deep convection, winds, and the rain, are key for enzodynamics. So what we can do now is to follow these variations at large scale. So this is a plot as a function of longitude and time. And these are the zonal currents extrapolated from tower moorings. And in white, these are the position of the convergence zone from hypothetical drifters. So we can follow the displacement of this Whirlpool Eastern Edge at large scale and long time scales. But in fact, the models indicate that this whirlpool migrates at intrasonal timescales under the influence of westerly wind events and MGO. So this is an example from a model at the onset of El Niño events. So you have here the wind stress, and you can see the huge westerly wind burst. In black, this is the eastern edge of the whirlpool. And if you look at the response, you see that deep wind bursts generate Kelvin waves that move the front, and also direct currents with a strong linear interaction at the front that enhance these displacements. So surface current observation would help to understand what drives this displacement, which are key, at intrasonal type scale. They would give access to advection, and so we could infer the contribution of heat fluxes. Okay, one of the last points is that in the tropical regions, you have very high precipitation and so a strong stratification in salinity at the surface with a thin mixed layer. And you have an example here, it's not very clear, of the response of the ocean to a wind burst. And I don't know if you can see, but there is a very shallow jet with a strong vertical shear. And as another example here, you see the mean zonal shear infer from difference between drifters at 15 meters and ergo surface drift. So you can see that there is a strong near-surface shear in these regions, and the presence of equatorial shallow trap jets. And surface currents would help to understand, to represent these jets and to understand the trapping of momentum. So I'm very late, or it's okay? Okay. So to finish with, here is an example of the island effects on the currents. These are plots around the Marquesas Islands in the tropics. And in this region of strong mean currents, you can see that the EKE from Oscar is very low compared to what we get from a high-resolution model with daily outputs. So there is a need in high-resolution surface currents around this island to understand the effect of islands on the fine-scale dynamics that impacts strongly the biology, as you can see here on a very recent chlorophyll map. But this would be very stringent because we would need resolution of a few kilometers. So as a summary, with the present observation system, we are limited because we don't have observation at the surface in the equator. We are limited to large-scale phenomenon, and surface currents from space would provide improved knowledge of the current variability at intraseasonal and mesoscale. So they would help to constrain SST, tracers budgets, by giving access to the upwelling intensity and variability at small scales, to the intraseasonal horizontal advection term, to the vertical shear, and at first order, an estimate of the turbulent mixing. They would help to better understand the dynamics of the frontal regions at intraseasonal timescales and the associated coupling, and that would help to better understand the trapping of momentum into the ocean. Just finish with open questions, maybe naive, but so Fabrice showed that this morning. there will be also very important challenges for SKIM, because there is a strong diurnal cycle, as you can see here on the plot he showed. So with the afternoon warming of the near surface layer, you have a strong diurnal cycle in currents with an important shear. So I think we need to discuss the implication for the orbit, the choice of the orbit and the repetitivity. Also, what we saw in this talk that there are very stringent spatial and temporal requirements needed to make progress in the processes we want to observe. So we should resolve these 40 days and 50 kilometers or less, and I'm not sure of what SKIM will be able to bring. And finally, it was also mentioned, but the tropics are regions of very high precipitation rate, and especially under the regions we want to observe. So, is it an issue with the K band?
Well, it is because of those come in the afternoon, 4 till 7 p.m.
Mm.
Yeah, it's good.
Okay, I'm done.
Questions for Sophie?
Yes.
Thank you. Very interesting. On the last point, this rain areas, that's also going to impact the upper layer in the ocean,
Yes.
both through the momentum exchange and the heat exchange. And are there any observations here that can show evidence of eventual how this freshwater layer sometimes can be very slippery
Yes.
and hence speed up
Yes.
and give us an observation from satellite that could be quite anomalous, but we don't know how to treat it unless we do have these complementary data that can support that this is an anomaly regarding freshwater.
Yeah. So you're certainly aware that at this location, under the heavier rain, there is a sparse experiment, and they are making a lot of complementary experiments, in-situ observations, to just study this sort of slippery layer. So I wanted to contact Tom Farah to know if there are evidence yet, but I didn't have time to do that.
Yeah, I mean, it's a comment on this whole issue of the tropics. Indeed, just your diurnal figure here, you know, you could label that in many ways, but, you know, winds, precipitation, clouds, everything builds up in the afternoon, and then just like the ocean, by 6 p.m., 7 p.m., for those of you that have sailed there, it's all over, you know, and then we start again early in the morning when the sun comes up. So that kind of afternoon is a killer. We have to deal with that. There are other missions that are being discussed that can help. You know, they're in development. They may not fly. The Copernicus Imaging Microwave Radiometer is one, which will be in a dawn-dusk arrangement probably. Can help. But getting back to Johnny's question, the whole game of the slippery layer, it exists.
Yeah.
And it depends what your science goals are. I mean, just because we don't measure it doesn't mean it goes away. What we really want is a geostationary system to look at those issues, because the world is the world. And we're always going to be undersampled, and we have to choose our target, and we focus on that. And as I think Ernesto mentioned earlier, we have, for the first time here, a programmatic setup in different countries where multiple missions can fly at the same time, potentially at least. And they all bring a little bit of a different cut and a different way of working. It's for us to have a little bit of a think over a glass of water and some peanuts about how we might want to phase those and how we might want to think of those synergies now, early on, so that we don't make a mess later and be accused of particularly heavy reviews when missions are killed, because we didn't think about that, and we can be killed by another mission. So I think we should get together at some point and have a chat and see what kind of processes that we should be aiming to try and catch, or the ones that we can definitely say to program managers, we're not doing that because of this, this and this, but we are doing this, and this is the reason why. That's the only way we can work effectively to cope with this kind of situation.
Yeah. But I think what's very important here too is that we have a diurnal cycle in the shear. And in the TPOS 2020 project, which is an international project in which we are rethinking the needed observations, we have recommendation to puts so very near surface observations of the shear at different places in the tropics. So this could also help to.
Okay, thank you very much.